So this is well, work in progress, I hope. It's a little bit different from most of the things I do. Usually when I do a project, I have a theorem and I'm talking about this, and this is maybe a bit more of an opinion or a reflection on things. Okay, so I'm going to be talking about Samuelson's correspondence principle. I'll sort of remind you to begin with what it is. So here we have sort of a diagram that I imagine is familiar to pretty much everybody. We've got a two-good economy. P is the price of the second good. So we've got a numeric good and we've got a second good. And on the vertical axis, we've got the excess demand of the second good. And so if P is very low, there's a lot of demand. If P is high, demand for the second good goes down. In the middle, we've got 3 points where the demand for the excess demand for the second good is 0. And by Walras' law, those are equilibria. Demand for the excess demand for the first good is 0. Okay, so if we think about what we would imagine to be the natural dynamics, there are two equilibria stable, and then the one in the middle is unstable. So by natural dynamics, I mean that if the excess demand is positive, price goes up. If excess demand is negative, price goes down. Okay. And now let's imagine shifting this curve up, which we imagine being some exogenous parameter changes, and so that the excess demand for the second good is higher at each price. And the point is that the stable equilibria, what we think of as the natural comparative statics. So you imagine that if the second good for some reason becomes more natural, more desirable, the natural thing is that its equilibrium price will rise. But you can also see from looking at the middle equilibrium that that's not a theorem that is true without some sort of additional assumption. Okay. And so Samuelson's idea was that if we develop some theory of economic dynamics, we would be able to say that the second equilibrium is one we won't observe, and therefore the comparative statics should be what we expect. Okay, for the relevant equilibria, the comparative statics are what we expect. Okay, so I'm going to give a quote from the Foundations of Economic Analysis, sort of reflecting where Samuelson thought the correspondence principle was. So he talks about the evolution of economic analysis. So it starts with Walras, who had the observation that basically there are the same number of equations as unknowns, and therefore you have the idea that economic equilibria are usually or typically, we now think of generically, determinate. So they're isolated, there are finitely many of them. You perturb the system, they change in a continuous manner, usually. Okay. Pareto, he credits with the idea of comparative statics. Although Pareto didn't talk about what he calls secondary inequalities, which I think are sort of second order conditions, and he credits that to other people, and then he puts himself in this line of people, saying that the final fourth step is the correspondence principle here. And so these were the days when you could write the history of economic thought in the first person present tense, right? And nobody would do that these days. Okay. So there was a lot of subsequent work over really the next 20 years associated. Arrow and Hurwitz were very important, and others, who thought about dynamic processes and adjustment to equilibrium. And so the conclusions of that research were kind of mixed. You could come up, so a particular Scarf came up with an example where any sort of reasonable price adjustment process would not stabilize the unique equilibrium of the economy. So in their book, General Competitive Analysis, Aaron Hahn have a rather harsh assessment of Samuelson's correspondence principle. So they talk about how they've reviewed various dynamic models, including ones that are kind of perverse in the sense that the auctioneer gets to kind of choose the price that will do what he wants, and then you can stabilize pretty much anything. But they come up with the idea that the correspondence principle really isn't a principle. Okay. So what I'm going to do is, I guess I should first of all say that this is in the spirit of looking at what Keynes said, where you don't really care so much what Keynes was thinking, but your interest is really to try and go back and look at what these people said and reflect on it from the point of view of more modern perspectives and more modern tools, and to try to
Can you just go one slide back?
Okay, yeah. We want to reflect on what these tools look like or how we should think about them in the light of sort of more modern methods or more modern perspectives, and try to extract what we think is really valuable here. And so I'm going to argue that, let's see, yeah, okay. That both in Samuelson and in Aaron Hahn, there's an identification of excess demand functions with dynamics, sort of automatic identification of the two notions that I think is a bit too fast. And if we take it apart, what's really important here is the idea that the correspondence principle can be thought of as advocating that the economically relevant equilibria are those whose fixed point index is 1. Okay, so I will explain. First of all, if you're going to have a principle that is general, you want to have a pretty general notion of what that principle is. And so I'll explain a very general notion of the fixed point index. And then I'll ask, I'll start out by asking, what do we get out of this principle? How should we think of its implications for what we do? And I'll have a quick but rather open-ended answer to that. And then I'm going to review the theory of the fixed point index, and also what's equivalent, namely the theory of the index of vector fields of the set of equilibria of a vector field. And so we want to ask, to what extent is this notion really a consequence, or in some sense a consequence, of a notion of dynamic stability? And here I'll be following working game theory by De Michaelis and Ritzberger and applying it to general equilibrium theory. What we'll see is that we will see that it is a consequence of stability with respect to pretty naive, I would think, or mechanistic adjustment processes. And I'll try to argue a little bit, but not really have too much, I think that's really convincing at this point, that this doesn't really fully capture our intuition about why this is a good principle. These adjustment processes are ones that we would currently regard as kind of silly or not really representing the way people interacting socially would manage to adjust things. Okay, but nonetheless, so in some sense, my advocacy of this version of the correspondence principle is really stronger than what I'm able to back up with any kind of concrete results at this point, and I'll suggest that's a challenge for us. Okay. So first of all, what does the correspondence principle give us? So okay, so this is going back to Samuelson. We think of that we've got a system of equations that characterize equilibria. So this would be excess demand equals 0 or something like that. So X is the set of endogenous variables. Alpha is some parameter. And so Samuelson thought of the scientific content of economic analysis largely as a matter of saying that some comparative static derivative had some definite sign. Okay. And so what we would say here is that what we think of as the correspondence principle is going to amount to delta being 0. I should say what these are. So we're looking at, say, the change in the equilibrium of variable x1 as we change alpha. And if you do the implicit function thing, write everything as in terms of matrices of partial derivatives, you get this equation. And here, delta is the determinant of the matrix of partial derivatives of f sub I with respect to xj. And delta ji is the ji cofactor. And so in this context, being able to attribute some definite sign to dx1 d alpha requires a lot. So we'll say that our principle is that delta should be greater than 0. That's our notion of the correspondence principle, what the fixed point index implies in the differentiable case. But then how is that going to apply some definite sign to that? Well, you need very strong assumptions here. A typical set of assumptions would be that only one of the partial of fi's with respect to alpha is non-zero, and so that and that you know the definite sign of that. And then not only do you need to know the sign of delta, but you also need to know the sign of the cofactor associated with that non-zero partial. So that's all very strong. What we find is that that happens.
Sign of cofactor be restricted by the fact that all metrics should be positively definite. Not all the delta should be negative, but the metrics of second derivative should be negatively definite, which would restrict the sign of cofactors.
So that is one important source of that information. So yeah, in certain demand systems, if you have an assumption that basically says that the demand of each thing depends strongly on its own price and then weakly on the prices of other things, that will allow you to say that the matrix of partials, in some sense, dominated by its diagonal, and that it would be.
Just second order condition says not more than sign of determinant. Says.
So for individual demand, that's correct. Yeah. So these conditions flow naturally out of second order conditions for optimization. For aggregate demand, they would typically not. Okay. Okay. Any event, what I'll suggest is that this is a very narrow view of what the scientific content of economic analysis is. We're all familiar with lots of models that analyze the world in a more complicated way, or if there are anybody who knows about econometricians here, they may be able to back me up that there are many econometric models that take a much more sophisticated view of what they're trying to do than the kinds of demand exercises that Samuelson will be considering, or very small ISL models or things like that. What I would say with respect to that is that in some sense, delta greater than 0 is only one piece of information. we have certain experiences where it turns out to be the critical step that allows us to say something definite. So this, in terms of its importance, I would say that Samuelson's correspondence principle has a difference, has an importance that's somewhat more extensive than what Samuelson thought. I would say that for comparative statics, its application is actually quite narrow, but it can be an interesting and important idea in other contexts as well. Okay. Okay, so now I'm going to move on and talk about the fixed point index. So we start out with this idea that if I've got a function here from 0, 1 to itself, we assign a fixed point of 1 if going from left to right, the function goes from above the diagonal to below the diagonal. If it goes from below the diagonal to above, we have a -1. In the generic case, the sum of these indexes will be 1. Okay. Now, so here I should say that this is what we'll be talking about now is the culmination of some mathematical developments, really beginning, well, I guess with Poincare, but in particular Lefschetz in the 1920s, and then developed in a more abstract manner. So culminating in the formulation I'll give in the early 50s. So the people here that are particularly important are Browder, who was one of the contemporaries of Nash, Harsanyi, all the other famous people who were graduate students in the Princeton math department in the late 40s, who, in a way I'll explain, pushed things to a much higher level of generality, and O'Neill, who came up with the axiomatic characterization that I'll present. Okay. So we want to generalize this notion of a fixed point index. And so I first of all have to define a quite general class of spaces. So we'll first of all have the notion of a retraction. So if you, a retraction of a big space Y onto a small space X, or subset X, is a continuous function from Y to X that has each point of X fixed. So you think of a big ball, you collapse it down onto a little ball. Okay. And we say that X is the retract of Y. An absolute neighborhood retract is a set such that whenever you embed it as a closed subset of a metric space, there's some neighborhood that retracts onto this set. One quite subtle but important aspect of fixed point theory is that this is really the set of spaces for which fixed point theory works. You should think of an absolute neighborhood retract as a space that is in some sense simple locally, because any point you could expand to a bigger space that then gets crushed down onto that space. So the big space would typically be a simpler space, and the simplicity is somehow preserved by this operation of retracting onto it. Okay, so for reasons, well, there are examples that show that you really need to restrict to these kinds of spaces to do fixed point theory, and that's what we're going to do. This is, for economists, this is a plenty big class of spaces, including many important infinite dimensional examples like the space of probability measures on a compact metric space. Okay. Second concept I'll mention to get to maximum generality is contractibility. So a convex set is contractible because you do a homotopy between the identity function and a constant function. Anything that's star-shaped, well, you have a star and you just pull everything back to the star. That's a slightly more general example. A circle is not contractible because you can't bring it back to a point only within itself. Okay. Okay, so consider a fixed absolute neighborhood retract X. That's where we're going to be working. We'll look at correspondences that have subsets of X as their domain. So let C be a compact subset of X, and let F be upper hemicontinuous and contractible valued. So the kinds of correspondences we're used to working with, except that we rarely see contractible valued ones. We usually just restrict to convex valued. Okay. And the set of fixed points of F is set of points F, X that X is an element of F of X. And we'll say that F is index immiscible if the set of fixed points doesn't contain any point on the boundary of C. So we take out C, take its closure. There are no points in the middle. You can sort of, if we go back to this basic picture here, you can sort of see why we need to do that. If we had some compact set that went like this, well, it's kind of ambiguous whether this point is firmly in that set or outside the set. So that's a restriction we need to impose. Okay, and we're going to let I be the set of index immiscible correspondences. So what's the fixed point index? The theorem asserts that there's a unique function lambda, the index, that satisfies the following property. Normalization just says that we can rescale these things as we like. So we'll agree that a constant function has index 1. Okay, which is, if you go back to the diagram, that's what we expect, right? The index is basically a local property. So it's something that's assigned to small sets of fixed points, and then to get the index of a bigger set, you add up the values on the small sets. Okay, so here we have our given F, whose domain is C. If we have compact sets C1 up to CR, the fixed points are contained in the interiors of those, then the index of F should be the sum of the indexes of the restrictions of F to each of the FIs. Okay, so again, so coming back here, I'd imagine that C1 was some set containing this fixed point, C2 is a set containing that fixed point, C3 is a set containing that fixed point, and I'm not sure if that's how it works, but the essential idea is, or the way to think about it is really that it's a local property, and moreover, you would think of this index as assigning a fixed point to this set, in the sense that if we take a smaller and smaller set of compact sets containing this point, we can really think of assigning the index to that set of fixed points and not to the set C that we sort of carry around as a way of encoding the idea that we have to be talking about some neighborhood that's well behaved. Okay. So that's additivity. The third property is continuity. So the idea is that if you perturb the correspondence, you don't change the index. So what that means concretely is we have the correspondence, we take some neighborhood of its graph, and if there's a correspondence that's admissible whose graph lives in that neighborhood, then it'll be the same, have the same index. What is the most common application of this principle, and often the way we think about it, is the idea of homotopy. So, yes?
So going back to that diagram, I can make the function wiggle a lot right around an index and keep the graph, stay within the neighborhood of the graph.
Do you want to go back to this basic diagram back here? Uh-huh.
So make the function bounce around a lot in a neighborhood, and it can have lots of fixed points.
Yeah. And yes?
So what's the continuity again?
So yes, so we're going to be, so this definition allows, so an admissible correspondence can have an infinite set of fixed points. It could have a set of fixed points that converges to here. It could have a whole interval of fixed points. And the assertion is that, well, you have to not have any fixed points on the boundary so that this whole set is kind of either in the interior, everything's either in the interior, or everything else is outside of the interior. But even if you've got infinitely many fixed points or a continuum of fixed points, we're going to still be able to assign an index to that set of fixed points. Okay. Whether, I mean, what's the meaning of that? Well, yeah.
Was assumption ruled out the identity function?
What?
The identity function on this, with a continuum of fixed points. What ruled out that as a possible F?
Okay, so if we have the identity function, so that would depend on what I took as x. So if I took the real line as my x, then the problem would be that I had a fixed point, these two fixed points on the boundary that were, violated the admissibility assumption. And that's kind of an important point in some game theory examples where you often get fixed points that are on the boundary of your product of simplices. And a common maneuver is to sort of expand things a little bit and combine that with some retraction that takes some open interval and pulls it back. So that we really think of the best response function as being defined on this open interval. And what we do to compute the best responses is pull points out here back to here, then map to the best responses of that.
So the no boundary is doing a lot of work here.
Yes, yes. Right. Okay. Okay. Any other questions? This is a good point for them. Okay. So a homotopy is, we think of it as a continuous function from the unit interval to the set of admissible valued correspondences, or we can think of it as a correspondence that has C times the interval as its domain. And it's an IAH, an index admissible homotopy, of if each HT is index admissible. Okay. And so we go back and we look at the continuity assumption. For each HT, we can take some neighborhood of the graph of HT. And for T prime close to T, the graph of HT prime will live in that neighborhood. And the consequence of that is that continuity implies that the index is a locally constant function of what I'll usually refer to as time here, T. And so a locally constant function on the unit interval is constant. So we have what you'll often see in the literature is basically the expression of the continuity principle, namely homotopy. That if you have a homotopy, the index at time 0 is the same as the index at time 1. Okay. Now, there's another, well, there are two other properties. One I won't mention, but one that will play a role in what we do. It's called commutativity. And I'll put it in a relatively simple form. The general expression of this principle is way too messy to present in the talk. But the idea is fairly simple. So you have, say, two functions, f that goes from x to y, and g that goes from y to x. And we can compose these in either order. So we can look at f composed with g, or g composed with x. And the continuity principle says that the index of those two is the same. So really, here we're sort of departing. Up here, we had a given ANR X. Here down here, we're departing from that framework and saying, suppose you have two different ANRs and you want to compare the indices on those. So what's really going on is we've got a theory that's valid for any ANR, and it satisfies this additional assumption. Okay, now commutativity was introduced by Browder, and so remember I stated the theorem, said everything's unique. In principle, commutativity you would think of, it should be a consequence of the other axioms. Okay, in practice that's not the case. In practice what Browder did was he proved continuity at a fairly low level, and then to generalize things used continuity to show that there was an index at a higher level, and then showed that it also satisfied commutativity. So he could walk up a letter of generality bringing commutativity as an axiom at each step. And so for that reason, I'll suggest you shouldn't try to really understand this as a consequence of the other axioms, even though logically it is. Okay. So I'm now going to talk a little bit about vector fields. So this is the context in which we're probably more familiar with the theory of the index. So we have some subset of Euclidean space. What's a vector field? Well, at each point there's some arrow pointing in some direction that has a particular magnitude. We can also put these on manifolds if you do a bunch of formal work. And so we have the same kind of theory here. So here we've got three equilibria, points where the vector field vanishes, and we assign an index to each one. Okay. So basically this theory is equivalent to the theory of the fixed point index. You might want to think of the function that we're assigning a fixed point to as, well, this point gets mapped to this point gets mapped to that point, that kind of thing. Obviously on manifolds, things get a little more complicated. In infinite dimensional spaces, more complicated still, and so forth. But that's the intuition. Okay. So whenever we have a vector field, that defines an autonomous dynamical system. So we've got a flow given at any point in this space, and any time t, I can ask, well, if I start here and follow the vector field, where am I going to end up at time t? That's the notion of a dynamical system, and that's really what Samuelson was thinking about. He was thinking there's some, passing very quickly from the notion of excess demand as a kind of vector field to an associated dynamical system and asking what are the properties of the equilibria of that dynamical system. What we can see here are that the two stable equilibria are the ones with index +1. Okay. But I should warn you that things aren't so simple. If I had a point that was a repeller, all the arrows were going in the opposite direction, that would also be an index +1 equilibria in this dimension. So certainly you can have things that have index +1 but are unstable. And something that's a little more subtle is that you can pass fixing an equilibrium, if you have a dynamical system for which it's stable, you can pass continuously to one for which is unstable through a homotopy of vector fields that don't change the set of equilibria locally. Or at least it depends on the dimension, but it's easy to make that happen. Okay. Okay. I'll often use the phrase inward pointing. The idea is that in order for this vector field, this dynamical system to be defined, whenever we're on the boundary, we have to be going into the set of interest. Okay, but yeah. So there's the definition. The partial of phi phi is called the flow, and it's uniquely determined by that condition that the partial of phi with respect to t at this point phi of p of t at time t is just the vector field. Okay. 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 So I'm now going to be aiming to give a quite general explanation of this relationship between the index and dynamics. So the first, I'm going to go through a series of definitions here that are from sort of basic to dynamical system theory. So set A is invariant when you start in A and you stay in A. So obviously an equilibrium is an invariant set, but you should think probably the example you should have in mind might be a limit cycle. So you have some cycle that just goes round and round. If you start a little bit inside, you converge going outward. Start a little outside, you converge going inward. Okay. A is stable if, okay, and there's some sort of subtle distinctions here I don't understand really that well. But the idea is that any neighborhood of A, say V, I can find a smaller neighborhood W such that if I start in W, I don't leave V. So that needn't imply anything about necessarily converging to A yet. I'm just saying that if I want to keep you from going outside of this big set V, there's some little set I can restrict you to start in, and you'll wander around in V, but not much more. Okay. What we're more interested in is the notion of an attractor. So A is uniformly attractive if there's some neighborhood V such that for any neighborhood W, any small neighborhood W, I can find some time capital T such that if I start in V and I let the system run for time capital T, that'll put me inside W. So here, attraction is uniform in the sense that everything in this set V is being attracted at a rate that doesn't really depend on where you start. There's some uniform bound on how long it takes you to get into W. Okay, so the invariant set is uniformly asymptotically stable if it is compact, stable, and uniformly attractive. So that's the notion of an attractor that we're most interested in. And I'm now going to talk about the relationship between this and a more familiar notion of stability, Lyapunov stability. So we have the notion of domain of attraction of A. So if I come back here, the domain of attraction of this point here would be everything to the left of the center here. So everything that eventually gets pulled into that equilibrium or attractor. And a Lyapunov function for D is, well, C1, I think it should be really Lipschitz here, but differentiable with respect to time. So you think of this in physical applications, you might think of this as energy or something like that. So if you're actually at the attractor, the value of the function is 0. If you're not yet at the attractor, the value of the function is positive. There's
Andy, on Douglas notation, there's an L and then there's a D inverse. Where did the D come from?
That's a good question. Okay, I think I'm a little bit. So this should be L here. I think this should probably be yeah. Okay, the slide needs to be fixed. Okay, so and I'll try.
VB is just the dynamic vectors themselves, the dynamic variables themselves. So L fixed or L is energy, and V is actually the dynamic variables themselves, and then so initial space of dynamic variables entire A, and then it's contracted.
Okay, I'm not sure, but okay. So I'll try to explain in words. I have to fix this slide clearly. Okay, but the idea is that the Lyapunov function takes the value of 0 on A, positive values away from A, and what this is trying to say is that you're always going down as you go forward in time, and going down in a way that doesn't allow you to asymptotically approach some value that's different from 0. So wherever you are, there's some sort of uniform bound on how fast you can be going down. You can't be going down so slowly that you don't ever get to A. Okay. Okay, the other property is that whenever we have a sequence of points that converges to something outside of A, then that sequence of points will be outside of D. So this, in some sense, says that we can run the system backwards in time and get to infinity before we leave D. Okay. Okay, so the main point, I should speed up. The main point here is that we know that if there is a Lyapunov function, then A is stable, because you're always going downhill. You have to eventually get to 0 in the limit. That's well known and easy to prove. A theorem that I want to alert you to is the converse of that. Okay, and this is a theorem that is quite sophisticated. It's not easy to prove at all. It emerged over a period of 30 or 40 years and was finally given its correct and proper form by a guy named Wesley Wilson in the late 60s. Okay, so this is a principle you should remember, because if you ever need it, come to me. Okay, so now I'm going to illustrate these ideas by basically applying the general equilibrium theory. And this is one of the arguments of the application of them to by D. Michaelis and Ritzberger to game theory. Okay, so set up some notation here. I'm going to have L commodities, so we'll be working in RL. Down here we're going to have the price simplex. So where does the price simplex live? It lives in the plane of price vectors who sum to 1. So E is this vector 1, 1, 1, 1. This inner product says the sum of the prices are 1. If you're actually in P, they're all positive. And H0 is the set of tangent vectors to points in P or to points in L. So it's the set of vectors whose components sum to 0. Okay, we've got an excess demand function. We want Walras law to be satisfied, of course. Okay. We want it also to be bounded below, and we want excess demand to go to infinity along any sequence of prices that goes to the boundary. We normalize excess demand by adding a certain amount of P to it, and the idea is that this preserves all the equilibria, but the sum of the components of this vector is 0, so zeta tilde is a nice vector field. Okay, and I remember before I said that there was something called the vector field index. Here we're going to actually say what it is. It's the fixed point index of alpha, where alpha is the function I get by taking P, adding this normalized excess demand to it. Okay, so it really is the fixed point index. Okay. Okay, we'll work with a compact subset of P whose interior contain all the equilibria. You can show that, by looking at a compact set that goes almost to the boundary of P, you get all the equilibria in there, and you can have the vector field be inward pointing on the boundary of that. So I'm not going to go into the details of that construction. Okay, so what do we mean by, okay, so here we're coming really to the, I think what's the critical difference between Samuelson's perspective and ours. Samuelson sort of, he was hoping we would figure out, we would learn, we would know what economic dynamics were. We now think that's quite naive, but we want to restrict to some kinds of dynamical processes, and we're going to do that in a way that imposes some restriction, but at the same time seems relatively agnostic about what the dynamic process is. So we'll say that natural price dynamics is a Lipschitz vector field that's inward pointing, and it vanishes everywhere that excess demand vanishes. So if you reach an equilibrium, you stop. And if you're not in equilibrium, then you'll adjust prices in a way that's sort of respectful of excess demand. So the inner product of the direction in which prices move with zeta or zeta tilde is greater than 0 for all p that aren't equilibria. So that gives us lots of room, lots of dynamical systems we could consider, but they have to, in some sense, be things that we could imagine as normal or adjustments to excess demand. And the claim here is that if nu is a natural price dynamics, A is asymptotically stable for that, and also a neighborhood retract. We need to impose that assumption here. Then the index of A is the same as its Euler characteristic. So this is, I should mention that the Euler characteristic of a set is the index of the identity function of that set. Okay. So in the case of a single point, the Euler characteristic is 1. So this is, say, if we had an isolated equilibrium, we'd have index 1. Okay. Okay. So I'll say a little bit about the proof relatively quickly, try to convey the intuition. Okay. First of all, these conditions here say that have the nice feature that if you take a convex combination of nu with p, you get a nice homotopy of vector fields that doesn't have any additional zeros. And we want to show that that the Euler characteristic of A is the fixed point index of A with respect to now not adding zeta tilde, but adding nu, and we can add any amount of nu. So we can multiply nu by some small delta, because it doesn't really matter. Okay. Second point here. We have asymptotic stability. Let D be the domain of attraction for A. Since A is asymptotically stable, it's also Lyapunov stable. So we can take some Lyapunov function. So this is a key step, one that applies Wilson's theorem. And so, a lot's going on here, but at this point it's very simple. Okay, A is also an A and R. So we have a retraction of some small neighborhood onto A. And we can actually take it to be the points that the Lyapunov function maps to the interval 0 epsilon for some epsilon. So we've got some nice small compact set. The Lyapunov our flow maps that set into itself because you start at any point in the boundary, and the Lyapunov condition says you're going inward. Okay. Okay, so nu is inward pointing on the boundary. Okay. So let's think about, this is the vector field rescaled by delta, and this is following the flow for up to time delta. So you've got this nice vector field. It's not changing very rapidly. It's Lipschitz. And so if you follow it for a little bit of time, that's pretty much the same thing. It's just going in that direction for a certain amount of time. So we can imagine doing a convex combination between following the field for a little bit and following the flow. And that also gives us an index admissible homotopy. So now we just have to show that the fixed point index, chi of A is the fixed point index of A with respect to this, with respect to the flow. Okay. So now we do the following things. We can follow the flow for delta, or we can follow the flow for a long time. And the map S to the flow at time S is a nice index admissible homotopy between those things. So we can move things up to some big time where the convex combination gives an index admissible homotopy between the flow at time t and that flow composed with this retraction. So now we've got a homotopy that maps onto A. And now we can run this backwards. So we've got this map S to R composed with the flow at time S. And we can run S backwards in time to get a homotopy to R composed with the flow at time 0, which is just R itself. Okay. So now we want to show that chi of A is the fixed point index with respect to R, with respect to this retraction. And at this point, we're going to apply commutativity. So we'll let I be the inclusion. And commutativity says that, well, lambda R is just I composed with R, because I is just the inclusion. We flip these things around. And now you've got the inclusion composed with R, but R brings you back to A. So that's just the identity on A. And this is, by definition, the Euler characteristic. Okay. So what have we done? Well, we've developed an interpretation of what we like about the correspondence principle that's quite general. It has the axioms. It's related to at least a naive notion of stability in a very general way, dynamic stability. How convincing is this? I would say not very convincing. We have lots of dynamical systems. We tend to think of dynamical adjustment in a much more sophisticated way. We imagine, arbitrageurs and speculators, playing a continuous time game that's being buffeted by new information. Somehow, we would like a model that explains, dynamical stability in those terms and gave explanations of why you would not observe index -1 equilibria, for instance, in terms of those. I'm sort of pessimistic about whether it's really going to be possible to do that. My sense of what will happen is that you want to say that you've got this -1 index equilibrium that you don't like. And you want to say that's not going to happen. So you build some big sophisticated game on top of it. Look at what happens in that big sophisticated game. Well, by virtue of general properties of the index, unless that game is dominated by very naive players doing fictitious play or something like that, then there's going to be an equilibrium up here that also has index -1. You're not going to like it because it has index -1, but that's the reason you didn't like the original equilibrium. You haven't really come up with something that much better. So to me, it seems that really giving a proper explanation of why we should never observe index -1 equilibria, that's a challenge that hasn't really been fully fulfilled. Okay. Certainly, in the literature on learning and games, there's no sophisticated model. And market microstructure is a different area that is very primitive at this point compared to that. Okay. So what would I say, sort of as a concluding point of view, instead of thinking of the correspondence principle in the way Samuelson did, something that's derived from economic dynamics, it's just for us an hypothesis. Okay, it's something that we can assume in the same way that we assume rationality. I would say that compared to rationality, it's pretty reasonable. Okay, it has some motivation, but this motivation does not yet capture the full strength of the intuition that supports it. How reasonable is it? I think it's very reasonable. Okay. We would be very surprised to see any stable social situation that we thought of as an index -1 equilibrium. Okay, so I hopefully we'll get down to the conclusion here. What have we done? We've looked at the history of this concept. We've tried to extract what's valuable. What seems to be most valuable is the idea that the only empirically relevant equilibria, isolated equilibria, are those with index +1. More generally, we can talk about components of equilibria, but that's not really so important. This can be justified or motivated by precise results that are quite general that give show that mechanical models of strategic adjustment lead to these kinds of equilibria. If they lead to anything at all, there's no guarantee that a natural price dynamic does anything good. This seems like a very reasonable hypothesis. Its consequences for economic analysis are, I think, rather modest, though not quite as narrow as Samuelson's view of economic science. But nonetheless, it's something that I think we can regard as sort of a stable and permanently valuable part of economic thought. Okay.
Thank you. Any questions? Yes.
So Hart and McLellan a while ago had a couple of papers about convergence to Nash equilibria in games, and the basic answer was that if you ask that what I do not depend on your utility function, but just what's happening, then it's not going to happen. That you can't get a decoupled dynamics in that sense. So, are there ways of restricting the dynamics in here so that, or should I be worried about any restriction? You've got this big set of dynamics. Do we want that big a set? Is basically. So they argued that decoupling is perfectly reasonable. What I do can't depend on something that I can't see that's inside your head.
Okay, so that's the same argument that economists were making about we can't observe people's utility directly, we can only observe their choices. And so in some sense it seems reasonable, in a different sense sympathy is an important aspect of human nature. Our ability to imagine the other person's point of view is really something we shouldn't neglect. It's very important. I don't know. So I would say that in some contexts that would be reasonable, particularly in evolutionary contexts where we imagine the strategies as just genes that reproduce in a mechanical fashion. The gene isn't going to have any idea of some other species or gene, what it wants or how it thinks. I guess I would also say that there are many circumstances under which we would expect that sort of sophisticated dynamics would converge to something more reliably than naive dynamics. So if you have any situation where a naive dynamics would lead to a limit cycle, then you expect that real people playing this who can learn, they learn what the equilibrium is and then they do that. But it's I think a research challenge rather than something we have really substantiated. And just generally, the boundary between where we should expect convergence to something and where we should expect chaotic behavior or just people don't reach an equilibrium and they don't know why. These haven't been settled, I think. many research challenges.
Okay, we'll stop there. We can obviously pursue the questions over coffee. On your behalf, I'd like to thank Andy for a very interesting talk. It's certainly removed cobwebs. Perhaps from you as well, so it's a good way to start the conference. Thank you very much, Andy.
Thank you.